Good day to you all. My name is James and I'm from Nelson Mandela University, particularly the Center for Broadband Communication. So I'm going to be speaking today about work that we have done with the team in making a number of solutions for different industrial applications, which range from clock and frequency dissemination to high capacity transmission in data centers and also in distributed fiber sensing. So this is basically work that we have done which is based on converging these technologies and having them embedded within the telecommunication network. So we all know of the connection within the network where we have the Internet of Things, where devices are all connected to the network. The various devices that includes our cell phones, our laptops, and even the television sets for television networks. And with this, it actually goes further to a case whereby most applications have gone on to consider cloud computing. And this has all been enabled with the advent of the 5G networks, which enable technologies like self-driving cars and all these other smart technologies. So with these technologies in place, we see that there is an ongoing increase in the need for high-speed communication. There is also an ongoing increase in the demand for high data speeds. So we see that with 5G networks, there is a data traffic rate of about 50 exabytes per month. And if we look at this graph, this is an exponential increase as compared to what has been ongoing in the previous years. So this exponential increase has resulted in a discrepancy between the demand and the capacity that the network can offer. So this is where we come in with the first solution at a data center, which is the central office, where we have switching technologies for different between different wavelengths in the data center. So in this data center, we have an 850 nanometer or the wavelength that is best within the data center is 850 nanometers. And if we are to propagate into the field where there is a need for switching between 850 nanometers and 1550, because when we are to do transmission into, like for fiber to the home and other functionalities, the wavelength that is used within the telecommunication system is between 1310 and 1550. So for switching between that wavelength, the technology that is available would require to switch or change first from the optical to the electrical, then back to the optical. And there's latency that is introduced by that kind of setup, which we have addressed by introducing a different technology, which is all optical switching, by simply pumping the 850 nanometer VCSEL, which is a vertical surface cavity VCSEL, right? It's a vertical cavity surface emitting laser, right, with the 1550 wavelength VCSEL, and giving an output in the 1550 range. But that output now can be controlled so that we can avoid channel collision. So the work that we have done goes further to show that this has been achieved by simply pumping with a 1550 on the 1550 laser source is first amplified, then the output is sent onto the 850 nanometer laser, and the output comes through the circulator from number 2. The output from number 2 can only go through 3, and this output from the 850 is in the 1550 range. So as we did this experiment, we would vary the bias of the 1550 nanometer laser, and would see that as the bias changes, which is the change in the bias shown there, the output from the 850 nanometer was also changing, which was a sign of us having successfully achieved all optical switching within the system. In the other section of our work, we went on further to look at frequency dissemination for stable optical clocks. These are very important for various applications that include synchronization within applications like the square kilometer array for the data that is received by different satellites. It's also important for the financial markets, for the banks. When someone buys shares, at times you really need to know at the specific time when a share was bought so that you can accurately determine the time and the calculations that relate to the time when the shares were bought. So in this setup, we have we have a frequency, a rubidium clock, which is a stable frequency clock, and a signal generator that is driven by it. And this gives us a signal that goes into the fiber. Our fiber is just a network which is 26 kilometers on this part of this schematic. So there is a reference signal that actually goes to the other end, and this is a feedback kind of system for controlling the actuator that controls the phase of this clock, because for the stability of the clock, we require a stable or a coherent phase. So when from the mixer, we have an error signal, because if the local oscillator and the RF that comes after the fiber have the same phase, our output there should have an error signal, which is our output should have an error signal which is, let me say, 0. But when there's a difference which is due to the phase induced by the fiber, then the error signal here will have a certain value that we can use to actuate the VCSEL and change the phase such that it comes to a point whereby the error signal goes to 0. So with this, we managed to make this system through an algorithm that dithers, meaning it controls the error signal to see if a step change allows a decrease in the error signal or an increase, and follows in the direction that allows the decrease in the error signal. So the green line on this graph shows the phase, which is the output from the stable rubidium clock, and the red line shows the phase, which is the output from our phase control. If the system is left without being to freely run without control of phase, the black line shows that the phase is not coherent, the phase is actually not stable. So we successfully showed that we can control the phase and have a proper clock dissemination for applications of this nature. So in the last part where we are converging these technologies, we have a setup where we also converged the clock and the data and transmitted them at the same time, all optical. So in this case, the clock is transmitted in the optical fiber, the data is also transmitted in the optical fiber, and this was achieved by modulating the data in intensity and also modulating the clock in the phase. And in the clock recovery, we saw that we can actually get a very stable clock output, and it had a good signal to noise ratio. So we successfully were able to recover the clock signal from a setup where we transmitted both the clock and the signal and the data. So in this setup, what we see here, the different lines are such that the green lines are from the data signal, the orange lines are for the clock signal, and the red lines represent the sensing. The sensing is based on Rayleigh backscatter, where you can monitor the sensing signal from the input end or transmission end of the network. So this will allow for a converged data clock and sensing network, because you would only monitor the sensing signal through the input end. So for the distributed fiber sensing at the input end of the network, we were able to measure a 73 hertz signal at 3 kilometers by using distributed sensing based on polarization monitoring. So when you monitored the polarization, we used pulses to transmit into, which are basically similar to the data pulses that you transmit inside the network. And by monitoring those pulses, the backscatter that comes from them was monitored and concatenated as shown in this diagram at the bottom right. And by taking an FFT at each point, which represents the length across the fiber, we're able to pick the appropriate frequency of the disturbance that occurs within the system. So with this, we have managed to make a system that monitors the latency for of these systems for latency sensitive technologies, and phase compensation enables the stability and coherence of these clock signals that is required for the various applications. And the wavelength switching, which is all optical, has also enabled faster or higher capacity data transmission. And with this, converging this with distributed sensors will actually help us have a system that can run or enable us to make a dense network of sensors on the fiber that is already deployed across the nation, or for better resolution sensing. With this, I thank you.